welcome to Math 10C Unit 1, Exponents and Radicals tutorial review. So, first of all, one of the topics we talked about was the real number system. So if you remember, I'm just going to draw you a little mini diagram. We had a real number system and it was broken up into two parts. So, if we cut it into a little diagram here, the whole thing would be called the real number system. Now that covers absolutely every number you need to know for the university. On this side, we've got a Q with a negative sign on the top. Who remembers what a Q with a negative sign means? Irrational. Good job. So that guy's the irrationals. Okay, the irrational numbers. So I would like somebody to give me an example. We use it all the time. An example of an irrational number. What would be a great example, Smitty? Perfect. Run on decimals. Well said. Run on decimal. No repeating. Okay, no repeating a pattern. Okay. Now, what creates those? What creates a run on decimal? A non-perfect square root. So if I give you root 17 and you type that in your calculator, you're going to get a run on decimal. So all non-perfect square roots and non-perfect cube roots, etc., will always give you run on decimals. Okay, they're irrational answers. So there's one more here that we've kind of forgotten about, but we use that button all the time. So what button have we forgotten about that is an irrational number? And it's special. It gets its own button. Ah, good. So we have the pi symbol. That's right. Okay. Now we're going to zip over to the other side. So numbers are categorized into basically the two categories. They're actually going to be rationals or they're going to be irrationals. They can't be both. Okay? You do not have a number crisscrossing over those. There's not a chance for them to be both. So these guys, if I take a look, we're going to have rational. Okay? Oops. A negative sign on top of him. He doesn't belong there. Okay. So we've just got rationals. He's the Q without the negative sign. So what are some examples of rational numbers? Rational numbers. What do we include in that box? Well, we've got our example of our boxes. What do we include in this box? What kinds of numbers? Okay, there's integers inside there. You betcha, there's that box. What else is inside these boxes? What else can I include in this set that doesn't go into any other set? Fractions, good. So we get fractions here. Okay, what else do we get? Good, we get two kinds of decimals. So two types of decimals. First kind is terminating. So 5.6, it ends. There's no numbers after the 6. There's one more kind of decimal we deal with. What other kind of decimal will we deal with in this category? Smitty? Repeating decimals. So repeating a pattern. It's got to repeat the same pattern. Okay. That is our largest box. Now we're going to go into our next largest box. It's a bit smaller. What fits in this smaller box? So I'm going to draw a smaller box inside this box. Actually, let's draw a circle. What could that circle represent? Now we're going back to our number line.
Negative and positive.
Negatives and positives. So that's our integers. So that circle is going to be all the integers. And that's going to go from negative infinity on your number line all the way to positive infinity. Okay? Only positive and negative whole numbers. No decimals, no fractions. All right. What's in that next box that fits inside all of them? What's this next box? Smaller set of numbers. We're shortening up our number line. Okay? Whole numbers. Excellent. We're going to put a smaller circle in there with a W. Okay? The W is the whole numbers. And that is from 0 to positive infinity. Okay? 0 to positive infinity. What is my teeniest box inside all of them? We also refer to them as the counting numbers. Natural, perfect. So we have natural numbers, and they're going to be our smallest circle. My diagram's small, so I'm going to make a little dot. That red dot there is going to be our natural numbers. Okay, and that's from +1 all the way to positive infinity. Okay, and the smaller the sets get, is meaning there's more restrictions on the types of numbers that can fit in those boxes. Okay, so our tiniest box, the counting numbers from 1 all the way up. Then we add 0, it's a bigger box. Then we add our negatives on the number line, it's even bigger, more numbers in there. Then we add the fractions and decimals, and we have an even bigger box. Okay, so those are our number systems that we're going to deal with. First one says decimals which are terminating, so it's an ending decimal. We know those are automatically rational, and they can be converted into fraction form. Yes, absolutely, that is true. That is one of the differences that we didn't talk about yet. So with our rational and irrational, if I just go back to that box for a minute, just comparing the two of them. So we've got the irrational numbers and we've got rational numbers. The really biggest thing about it, that's the biggest difference, is these rational numbers can be put into fraction form. We can make any number into a fraction by putting a 1 underneath it. And we can math frac a lot of ones that will go into lowest terms. However, these irrationals can never be put into fraction form. That's the whole point why they're irrational. Okay? They cannot be put into fraction form. Okay, so I'll give you a minute to write that down so you don't forget. Repeating decimals cannot be converted into fraction form. That is false. So the first one's true, that is false. Repeating decimals definitely can be put into fraction form. And it's like this. If I've got 0.3 repeating, what I do is I take that 3 and I see what place value it's in. This guy is in the 10th place. The 10th place. So I put a 10 underneath. The thing that changes is if you have a repeating decimal, you need to subtract 1 from the bottom. So the bottom number is actually going to be a 9 for any repeating number. So 3 over 9 is 0.3 repeating. We math frac it down into 1/3. 5 over 9 will give you 0.5 repeating. 4 over 9 will give you 0.4 repeating. 7 over 99 will be 7 repeating. Okay? So that's how repeating digits are put into fraction form. So yes, they can be put into fraction form. We just subtract 1 from the bottom. Okay. That's how that part works. So the first one's true, the second one's false. All right. Next we've got only decimal numbers which can terminate can go into fraction form. Well, that's false because we just figured out that repeating decimals can be put into fraction form. So we've got true, false, false. Rationals are either repeating decimals or terminating decimals. Is that true for rational numbers? Yep, that's true. You're either going to have repeating or terminating because any digit, can remember, can be put into a decimal or a fraction. Okay? They just forgot the fractions in that statement. But they're wondering, is that statement true? Yes, that statement is true. Okay? It didn't state everything that's in that category, but it stated 2 things that work. So yes, it's true. So decimal numbers can be repeating and non-repeating at the same time. Huh? That's confusing. That's false. Okay? You can't have a number that stops and then all of a sudden starts to repeat. Okay? That doesn't happen. That's driving. Okay. Pi is an irrational number? Absolutely. We do know that's true. Okay. The one thing we have to remember, we're going to move down to the chart below. The one thing we have to remember is when we're working and trying to categorize numbers, we always need to simplify it. So if we just move down, this is square root 49. Well, we need to solve it first if it's possible. Well, that's going to give us a 7. So you always solve it first if possible. Then you find out what categories it fits in. Well, the 7 is a counting number. So it's going to fit in the naturals. And if it's in that baby box, it's in all the bigger blocks above it that fits into it. But remember, if something is rational, it can't be irrational. Okay, so you're never going to check those two boxes together ever, ever. And everything is a real number. Okay, absolutely everything. Now, this one, you would math frac if possible. It doesn't math frac down, but it is a fraction. Now, some might say, hey, Miss Tuck, it's got a negative sign. Isn't it a integer? No. Integers can't be fractions. They're on the number line, but they're only the negative whole numbers and positive whole numbers. No fractions, no decimals in the integer category. Okay? Pi, he's that irrational one, running on forever. Here, this fraction here, you can solve the fraction. It divides evenly 5 times. You're going to get a negative 5 for an answer. So, you look at where negative 5 starts. He's an integer. So he would start in our integer box. And then he'd be the boxes above it. So he'd be the integer box and the rational, and of course he's a real. Okay? The others should be quite straightforward for you to figure out. So outcome 1.2 is talking about prime numbers and their applications and common multiples. Least common multiple and greatest common factor. So we're going to talk about each one of those. So we need to list the first 10 prime numbers. Well, when we have a prime number, what is the definition of that? Who remembers what is a prime number? Okay. So a prime, very well said. So a number that is a prime number cannot have only 2 factors, but they have to be different. 2 different factors. And that's why on number 3 here, it says list the first 10 prime numbers. And really, that's out of order. It should be 1, 2, 3, 4. But anyways, the second question there says, what is a prime number and why are 0 and 1 not prime numbers? Well, prime numbers are numbers that have only 2 different factors. And they are 1 and itself. Which is why the number 1 and 0 are not prime numbers, because there's no other different number to multiply them by to get their answer. So to get a 1 as an answer, you need to take 1 times it by itself, 1 times 1. But the key here is they need to be different factors. So that's why 1 and 0 are not prime numbers. So our very first prime number, and one of our only even prime numbers we start with is 2. Good. So 2 is a prime number, 3 is a prime number, 5 is a prime number, 7 is a prime number, 11, 13, 17, 19, 23, and 29. Okay? Those are our first 10 prime numbers. Okay, we want to find the least common multiple of 8 and 12. Well, least common multiple is basically saying we want a lowest common denominator of a fraction. We find it the exact same way. Okay? So, between 8 and 12, what numbers would both of those divide into where I could create a common denominator if I had to, is what we're doing. So what you do is you create a factor list, okay, a prime factor list. So we're going to do a factor tree for each of them. So here's our prime factor trees. So I'm going to do the H right here. So you start dividing by 2, of course. If it's an even number, you start dividing by 2. If it's an odd number, you start dividing by 3. So 8 is 2 times 4. Circle the prime number. And 4 is 2 times 2. So that means I could write 8 is 2 times 2 times 2, which is 2 cubed. Next, I'm going to do 12. I'll do 12 right here. Divides by 2, and a 6. A 6 divides by 2 with a 3, and both are prime numbers. So 12 becomes 2 times 2 times 3, which is 2 squared, times 3 to the 1. Now we need to put them in this format when we want to find the least common multiple. Because the least common multiple states as a rule, you will take the one with the highest exponent from that set. So I have a set of 2's. I'm going to take the one with the highest exponent. So I'm going to take 2 cubed as part of my answer. Then I take every other number that's there if there's no other pairing. So 3 to the 1, he's got no other pairing, so he's got to come down as well. So times 3 to the 1. That will be my least common multiple. So I'm going to multiply that out now. So that's going to give me 8 times 3, which is going to give me 24. So that's how you find it using prime factorization. I will give you a different example in a moment, but I'll do it in this format already, and then we'll figure it out. Okay? Okay, here's another example of least common multiple before we move on to greatest common factor. So for a least common multiple, I'm just going to write a couple different ones in factored form already. So if I've got a number, I've got 2 cubed times 3 times 5 squared times 7. My other number is going to be 2 squared times 3 squared times 5 times 7 squared. And we're going to put a 9 on the end. All right, those are my 2 sets of numbers. I don't know what the numbers started with. I didn't figure that out. I'm just pulling stuff off the top of my head here. But what I'm showing you is, when you line them up, you match them according to the numbers they have a matching pair with. So these guys are a matching pair. I take the guy with the highest exponent. So I'm going to take this one. So 2 cubed comes down as part of my answer. I look at the next pairing, and I see 3 squared is the larger one. So I'm going to take 3 squared. I look at the 5 pairing. 5 squared is larger than 5 to the 1. So I'm going to take 5 squared. Over here, same thing. I have a 7 to the 1 and a 7 squared. So 7 squared is bigger. I'm going to take the 7 squared. And 9 by itself, it doesn't have a pairing, so he's got to come along anyway. So we're going to times all that by 9. So the answer of all that, it's going to be a very huge number, but the answer of all of that will be the least common multiple for those 2 large numbers that I started with. Okay? And that's how you find it. You put them into the order and find the matching ones with them. Okay? Now we're going to talk about greatest common factor. We have 36 and 48. So again, we do our prime factorization. Or we can just do the factors, list the factors of 36 and 48, and find the ones that they have that are the largest. So there's 2 ways to do it. First way is the prime factorization with the factor trees. I'll show you that way first. So 36, again, we start dividing by 2 because it's an even number. 2 times 18, circle the prime number. 18 divides by 2, 2 times 9, circle your prime number. 9 divides by 3 evenly. They're both prime numbers. So 36 becomes 2 times 2 times 3 times 3. I'm going to do the exact same thing for 48, and I'm going to write my number underneath it. 48, I'm going to put over here. Again, it's an even number. Start dividing by 2. Circle your prime number, 2 and 24. 24 divides by 2, 12 times. 12 divides by 2, 6 times. 6 divides by 2, 3 times. We end up with 2 prime numbers at the end. Now we're going to put all of our numbers listed. So 2 times 2 times 2, 4 2's times 3. Once I've got my list, we don't need to put it into the form we did for least common multiple. We don't need to put the exponents on them. We don't need to know how many there are. All we're going to do is we're going to circle the matching ones. So, the ones that match, I have 2 2's, they match. I have another 2 2's, and then I've got 2 3's. That will be your common factor, your greatest common factor. So my answer will be 2 times 3, which is going to be 12. Okay, that would be your greatest common factor for that question. The other way to do it is to draw a factor list, like we do when we're factoring. So it's to draw a factor list. Okay, now we're switching gears. We're going to talk about radicals. Perfect squares, perfect cube roots, and non-perfects. So we've got such things called an entire radical, and we've got things called a mixed radical. Entire radicals will have everything under the radical sign. So if I've got root 12, that is an entire radical because nothing is out front except for a hidden 1. My coefficient is a hidden 1. That's how you know it's an entire radical. Okay, you want a hidden coefficient of 1. If I've got 2 cube root 10, okay, 2 cube root 10. Because there's a number out front that is not a hidden 1, we now call that a mixed radical. Okay, it's a mix because there's something out front that is not a hidden positive 1. Okay? If you've got a negative sign out front, that means there's a negative 1. Then it's a mixed radical. Okay? All right. Now some, remember, we can't put negative signs under even indexes. So if I had a negative root 12, the only way I can write negative root 12 is to put my negative sign out front. All the entire digits are underneath, the radicand is here. However, you need to keep that negative outside because the index, in the little check mark part we call it, the index in there, when it's an even number, negatives have to be outside, always, 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 they're never inside. Okay? In a mixed or an entire, they're never inside. So if I've got fourth root, negative fourth root 16. This guy right here, he's a negative. Fourth root, it's an even index. You leave that negative sign out front. Okay? Let's go 18. 16 is a perfect fourth. Okay. So, the number in the check mark part, that's called the index. We have our little purple pages, which you're allowed to use on your final exam. Okay? You don't have to bring them into your final exam. They will be stapled attached to it. Okay? So you don't have to worry, they will be there for you. So, if we want to know what is the value of each expression, that means we actually try to put it in our calculator. So, on our purple sheets, we have lists. We have perfect square lists, we have perfect cube lists, we have perfect fourth lists, and fifth lists. That's what we're going to use when we try to break them down. Okay? If they are perfect squares, we can easily put them in the calculator and get our answer. So root 16 will give us an answer of 4. Root 144 will give us an answer of 12. However, these are not perfect squares. So if they're not perfect squares, you leave them like that in simplest radical form. This one is not simplest radical form. I would change it. But this question is actually telling us to solve it to 2 decimal places. So we would actually put it in the calculator and solve it. Okay, so root 18 to the nearest 2 decimal places. Sure. Over there. 4.24. Good. 4.24. Perfect. Root 33. Root 33. 5.7. Good. 5.74. Beautiful. All right. Let's move on to the next part. These are the types of questions where the words can mess you up. So we have to understand what this part means. The square root of a number is 13. That means I've got something under here and the answer's 13. How would I find out what answer would go underneath? What would you do to find out? I'll give you a hint. You work backwards. Okay, you work backwards. Exactly. So whatever the index is, you take a look at the index. This one's telling us it's a square root. So the index is that hidden 2. So you're going to put that index on as an exponent on the digit. So this is actually 13 times 13, which is 169. So the number under here would have been 169. Okay? That's how you would do that question. Now we're going the opposite in the next question. And they usually put these ones into our measurement unit, which is why we have unit 7, and it's throughout all of the units, because there's always measurement, there's always perimeter, there's always area, okay? It comes all the time. So on the next question, it's telling us the area. So instead, it's telling you the larger number, like this one here. It's telling us this one, and it wants to know what number was multiplied by itself. It's basically what it's telling us. So, if we take a look at that number 9 there, the area of a square block is 24 meters squared. So when you know area of something, and if it's a square, that means you need to do the opposite. You square root. So to find the side length is equal to the square root of the area. So that means my side length is going to be square root 24. Okay? So you're square root 24. Now, if it doesn't tell you to round the decimal, that means it wants you to reduce it to a mixed radical, lowest mixed radical in simplest form. Okay? So we need to reduce this, and we're going to talk about that in a moment here. Okay, we're continuing number 10. It's talking again about an area, and it's talking about a square. So, area is 80, side is going to be root 80, and I need to reduce it. But this one says, calculate the length to 1 decimal place. So, square root 80 is going to give me 8.9. That's 1 decimal place. So it says, how much fencing would be required to enclose the lot? Well, if it's a square, that means all sides are the same. It's asking for the perimeter. So here's my square, and if you have to draw yourself a diagram, it's a good idea to do that. You've got 8.9 all around because they're all the same size. It's a square. So part B is actually asking for perimeter. So you're going to take 4 sides that are identical and times it by the side length, 8.9. Okay? And that's going to give us 35.8. And again, we use our units, meters, and it's perimeter, so it's not meters squared. Okay, it's perimeter. All right. Before we move on to question 11, because question 11 is dealing with mixed radicals, we need to be able to figure out how to reduce them and how to create them. Okay, there was a question about why is this only meters, whereas area is meters squared. We can think of it this way. With area, you need to take 2 dimensions and you're multiplying them. So it's a length times a width, there's 2 dimensions, 2 things you're multiplying. So that's where the squared unit comes from. Now, the perimeter, yeah, we're still multiplying, but really, we can just add it all up all the way around. Okay? So it's the distance around. We're using one number or one side length, or every side length. They could be all different depending on the yard you have or the area you're enclosing. Okay? They don't have to be squares. We're just dealing with simple little squares here. But the reason that it's not meters squared is because it's perimeter. We're using one dimension. Okay, it's a one-dimensional thing. We're measuring length. We're not measuring length and width. We're measuring length of each side and adding them up. So that's why it's m exponent 1. Okay? All right. Let's move on now to figure out how are we going to create mixed radicals and entire radicals. So a little brief reminder on that. So a mixed radical, if I've got a mix, we're going to go mixed to entire. If I've got 4 root 2, and I want to create a mixed radical, we're going to work down. So I want to create a mixed radical. Here's our steps. What you do is you take the number out front, and you're going to bring it underneath the radical sign. He's going to slip in front of that guy right there, and he's going to multiply by that guy, but not quite yet. Because when he slides underneath there, he's going to grab this index and he's going to use it as an exponent. So this guy becomes this. Under our root sign, a 4 comes down, we had our 2 in there originally, and we have a hidden 2 for an index. So that 2 is going to slide across and go as his exponent. And that is a must. So whatever this index is, it's going to be the exponent on whatever you bring inside the root sign, the radical sign. And now you would do BEDMAS under the radical sign. So under my radical sign here, I've got 4 squared. So the 4 squared becomes a 16. I bring my 2 down, times 2. Now, if you want to do it all in one step, you can type with your calculator, 4 squared times 2. You're going to get 32, and that's just fine. I'm just showing you how each step would be calculated. Okay? And you'd end up with root 32, and that will be your final answer. Okay? So that's how you bring something inside. Now, remember, if there was a negative there, if I've got a dangling negative, that negative is going to stay out front because it's an even index. Okay? 2, 4, 6, 8. Because even index, that negative sign stays outside. We're going to do one with a cube root now. So I'm going to have 2 cube root 3. 2 cube root 3. And I'm going to make that 2 a negative 2. Because it is an index of an odd number, okay, it's a 3, it's an odd number index, that means the negative can go inside with it. So that means I put the 2 with the negative in a bracket when I bring it inside. So now I'm going to write my radical sign again. Don't forget your index. If you forget your index, it's completely wrong because that means you're talking about a square root. They're very different. Square root means you took one number and times it by itself. Over here, we're going to take one number, we're going to times it by itself 3 times. Here we just times it by itself 2 times. That's a big difference. So we've got our negative 2 coming in. We put the index on. He's going to slide over as an exponent. He still stays in his checkmark part. But he's going to slide over and be an exponent on what you brought in. Then you're going to multiply by what was already underneath there. And there was a 3 underneath there. That's where you're going to multiply it to 3. So continuing on, finishing this question, I have my cube root. I'm going to solve my negative 2 cubed. That's going to give me a negative 8. I bring my positive 3 down. I multiply those now, and that's going to give me cube root of negative 24. And remember, yes, the negative sign can be underneath because you have an odd number index. Number 11, it says the diameter of a circle is given by this formula. It says the D is diameter and the A is the area. It says find the diameter of a circle with an area of 175. So all it wants you to do is plug in the 175 into the correct variable. You have 2 variables here. You've got a D and a capital A. So you're putting that 175 into one of those spots. It tells us D is diameter and we're solving for D. So that means this number is going to go where the A is. So I'm going to have 113 root 175. And that's how I'm going to find my area. Or sorry, my diameter. Pardon me. That's how I'm going to find the diameter. So you just literally multiply it out like that. You're going to type in your calculator, 113 root 175. You're going to get 1494.8. And again, use your units, centimeters squared. So telling us centimeters squared. Okay, we've talked about a lot of stuff. We've talked about going from mixed to entire. Now we need to talk about entire to mixed as our last step. Now we're going to go from entire to mixed. And this is a necessary step because mixed is considered to be simplest form of any radical. So this step is essential. You need to be able to do this. Okay? So entire to mix. We'll do two examples. One will be a cube root and one is going to be a square root. So I'm going to take root 180. Now, we try to find the greatest common factor to divide it by, but what we're actually looking for is we're going to look on our purple sheets and we're going to find the index. So our index is a hidden 2. So I'm going to be looking on my perfect squares list, and I'm going to divide that 180 by the perfect squares that are smaller than it. And I'm going to divide it by the ones that don't give me a decimal answer. So I'm just going to pick one of them. I know that 18 will divide by 9, so that means 180 will also divide by 9. So I'm going to break this down. This guy is equal to root 9 times 20, root 20. So you always put your perfect square, your perfect root first, and you solve it. So root 9 is a 3. He comes and sits beside the other radical that you have left over. Root 20. Now you check and see on your purple sheet. Can root 20 be broken down further? Yes, it can. 20 can divide by 4. That is a perfect square. So I break this guy down again. The 3 will come down in front. Root 20 we said divided by root 4 and 5. So 4 times 5. And 4 is the perfect square. We always put the perfect square first. We put our perfect square first so that we can solve his answer when he's sitting beside the other coefficient out in front. So the 3 comes down. I'm going to solve my square root 4, which gives me a 2. Remember, they're multiplying because they're sitting side by side. That doesn't become the number 32. It's 3 times 2. And the root 5 does not break down lower. He's as low as you go. So the only thing you can do now is just multiply the 2 numbers out front. So, multiplying those, I'm going to get a 6 root 5 as my final answer. Okay? Next, we're going to talk about cube roots. Okay, we're going to go with cube root. Whoa. The cube root of 80. Now we're going to look at a different column in our purple sheet. We're going to be looking at the perfect cubes because that's what our index is. It's a cube root. So we're going to find that 8 is a perfect cube. So we're going to put our perfect cube of 8 first, and 8 times 10 gives me 80. 8 is our perfect cube, so we actually solve it. We type in our calculator and go cube root 8, or we look at our purple sheet, and his answer is 2. He's sitting beside, which means he's timesing by what's left over. Cube root 10. Now, you have to show that time sign there. No, you don't, because automatically when something's sitting beside something else, it means multiply. So your final answer for this question is going to be 2 cube root 10. The 10 cannot break down by any other lower cube roots because the lowest cube root is cube root 8. Okay? This concludes Part A of Unit 1, Radicals and Exponents.